Welcome to the 17th video of this course on quantum processing. Last time we talked about the idea of Feshbach resonance and how can we get, for example, crossover between Bose-Einstein condensation to the state of the crossover in between the BCS wave function. And we indicated that the Bose-Einstein condensation is just about bosonic superfluidity. And for the nice BCS Cooper pairs wave function, it's called the fermionic superfluidity. And we can tune the interaction between the magnetic field and the atoms, and you can go from one state to the other. Today we are going to engineer what we call the optical lattices. And optical lattices are a very interesting model to build a quantum simulator. So if you have a condensed matter problem that looks like this, okay, and you have wave function, periodic wave function, or periodicity of atoms, and wave function psi, that's electrons and a lattice, this is normally the solid state problem that you have. But in quantum mechanics, we are going to introduce the idea of simulating this model by the optical lattices. And imagine that you have periodic potential of light instead of atoms, and you load atoms in the potential of light. This is what I call the optical lattices, and you load atoms on the potential of the optical lattices. This is exact quantum simulation of condensed matter problem, and even extracting many information that you cannot extract from any solid state or condensed matter problem in the normal setting. So this is considered to be a quantum simulator for electrons in solids, okay, atoms in lattice, and you can in fact study many interacting problem. Here it's a many-body system, okay. You do some mean field approximation for a solid state to extract the mean field of the electrons in a lattice, in an atomic lattice. But here we do not do mean field approximations or mean field problem. And in fact, if you have some atoms in this lattice, as you see, I load some atoms here, you can study strongly interacting limit of physics here. So once you load Bose-Einstein condensation, so now the interaction actually between the lattice sites maybe dramatically increases or decreases according to how you play with this. And this model for optical lattices is very convenient for studying strongly interacting physics. So let us remind ourselves of the band structure in a solid state problem, and here periodic potential of atoms, for example, but we will replace them by light. But remember that the band structure and the wave function here, the wave function is a Bloch wave. So the Bloch wave function or the Bloch wave function waves are eigenstates of the Hamiltonian. And remember that the Q is the quasi-momentum state. Once you talk about lattice, you start to replace the momentum by the quasi-momentum, or call it crystal momentum at some point. And the n is the band index that you are interested in during the oscillation, during the wave function oscillation. And and the energy eigenstates of the Hamiltonian are looking like this. And the Hamiltonian of the Schrödinger equation is actually the kinetic energy plus the potential energy operators here for both. If you look at the other side, let's make sure that we uncover the lattice, and the lattice wave function for you here, the Bloch wave functions are the self-periodic part of the oscillation here. I just forgot the Q. This is the Q for the quasi-momentum state and for n band index that we have, and the envelope wave function for the exponential here, also part of the Bloch wave function. If you solve this for if you solve this for the Hamiltonian, and you write the Hamiltonian for such a Bloch state for the lattice, you find that just you add another term for the quasi-momentum state for here, because it's a lattice and we have the lattice, the potential of the lattice. Okay, So let us try to write down the potential and the wave function, the eigenstates of the Hamiltonian by this way, that is we call the Fourier expansion. We start to make Fourier expansion here. Okay, and if you write down the potential, you can expand this potential just for R. If you have many lattice and you have the potential, then you can expand this by the exponential Fourier problem, and this Fourier problem will get me to this exponential. And for the wave function, I always forget to write the bend index. So here, yes, for n and a q, and okay. So, and also for n. Okay. For here, if you have the wave function that looks like this, you just expand over the lattice, and the lattice just here the wave function for the exponential over the lattice. So we get the first term of the Hamiltonian for the Schrödinger solution. We just expand over the lattice here, just the wave function, and also the potential energy, and you can expand for all the bases here for R and L for the lattice. And also, if you would like to write down the kinetic energy part of this, you just see that you have these terms to factor of 2, because in fact you have h bar k at some here. If you have q crystal momentum and you're here minus h bar k, you can look at those nice diagrams for the wave function here, some stuff like this, and you have the modes. You can look at the modes, and you can extract the kinetic energy to be written like this in format this, and because we have 2 h bar k and L, and you can find this step like this. So we are interested in coupling both to get the Hamiltonian. The last time the Hamiltonian for the lattice, and this Hamiltonian looks like this. Okay, this Hamiltonian looks like this. And in fact, this Hamiltonian is important for the lattice, and we will see in a second for the case of the optical lattice. So let's make our story much fancier here, and we talk about how we can superimpose optical lattice, how we can combine light together to form the optical lattice. So the optical lattice can be formed in any kind of direction, in any kind of dimension you would like to. So here we can superimpose optical waves, standing waves for periodicity here, lambda over 2, and you can create 1D lattice. So the potential, or there's a potential here for the lattice, it's just the sinusoidal oscillation. Just for example, if it's a cube, so you find x, y, z. If it's a cubic lattice, it's triangular lattice, or whatever, quasi crystal lattice, you can build whatever kind of lattice you want to build. So the possibility also to create super lattices. You can get super lattices, and those super lattices are just with controllable phase and an amplitude, and you can get something like this, for example, and just non-symmetric of wave function for super lattices by superimposing different amplitudes and phase, or we're just manipulating, for example, the phase and amplitude for both superimposed waves. You can actually create fancy lattice. You can create quasi-crystal structure. You can create triangular lattice, whatever kind of lattice you would like to build. You can engineer what kind of lattice you want to study the problem of interactions in a controllable manner. And in fact, as we saw, we load ultra-cooled atoms on optical lattices. We will see next time this important model of superfluid mode transition. You will see this in the next video, that you load ultra-cooled atoms and you control the interaction between the lattice sites. Let's see this important definition for Bloch waves in superposition state. So if you have the lattice and you start to tunnel the Bloch waves from one side to the other, now you have complete superposition state between the Bloch waves. This is what we called the Fourier function. The Fourier function We call it the localized Vanier function. They are localized, and they are in fact considered to be localized like Gaussian solutions, the Gaussian eigenstates of the Hamiltonian. And they are, in fact, they are Gaussian, looking like Gaussian wave functions of the harmonic oscillator problem that you can uncover. So the Bloch waves, let me remind you that the Bloch waves that we have are like the plane waves, but the Bloch waves for a lattice are like the plane wave of free space. Okay, you have free space and you have the waves in the free space. They are in fact similar to the Bloch waves in a periodic potential of light or atoms or whatever. So the Vanier function are the idea here for Vanier function, localized Vanier function, that you can just expand the Bloch waves and just superposition between the Bloch waves, and you can see it like the summation for I and the exponential and the Bloch wave function for quasi-momentum state. Let me tell you that the Vanier function are just a result from tunneling from one side to the other. If you have Vanier function on this side and you can transfer to the other side by the matrix elements of the Hamiltonian, this is exactly what we will begin to see quantum simulation with. So you can write down the kinetic energy or the tunneling of the system of the wave functions like this way. So if you have the J we will call it here the tunneling energy. And if you just divide J over H bar, you can get the tunneling rate. Anyway, so you will hop from one side to the other by the matrix elements of the Hamiltonian, you integrate, and in between the Hamiltonian is nothing else than kinetic energy plus potential energy. Okay, so you can tunnel like this. Okay, you can tunnel like this, and you can also interact. So you can interact between lattice in one lattice side. You can interact by this way. If you have some wave functions that are localized in one state, they are in fact like interacting with a, let's say, a delta function and one delta function here, and you can see that we can, if you have two, for example, then you have the wave function, the probability is squared, so you have W of x all over 4, and you integrate over the whole volume here. So the J here, what we call, and you can see J here many times in pseudo potential problems in the condensed matter system. It's 4 by H bar over M. Okay, so in fact this also have AS, and the AS here, let's say, okay, this delta function that I talked about. AS here, this is the scattering length between the atoms. We introduced the scattering problem before. So now you have the interaction term and you have the tunneling term. Then we can build optical lattices and load ultra-cool atoms, and you can start tunnel from one side to the other. Let me tell you that this model is an important model for studying condensed matter. Let me just, because I do not feel rest with this, it's not comfortable for me. This is H bar square. So you can get from localization to delocalization systems for tunneling the wave functions, and you can express this in terms of optical lattices, and this is considered to be a fertile base for building quantum simulation. Next time we will build a model, an important model in the field, and we will see the importance of these quantum simulation problems. Thanks very much for your watching, and let's see you in the next video.